Here we have another sample problem. So it says a solenoid has an inductance of 53 millihenry and a resistance of 0.37 ohms. If the solenoid is connected to a battery, how long will the current take to reach half of its final equilibrium value? Final equilibrium value. Okay, so here we can simply recall actually the I is actually equals to something like E over R and then 1 minus exponential to negative T of T, I think it is RT over L, something like this, or you can consider it as T over tau L, okay, something like this. Yeah, so it asks you what is the time, how long will it take to reach its final equilibrium value. So at the beginning, when T is 0, this thing is 1, okay, 1 minus 1 is 0, okay, and then finally when T tends to infinity, this is 0, so finally this is 1 minus 0 is 1, so it's somehow like from 0 to 1 without considering this factor, okay, so it's like goes from 0 to 1, so half of this equilibrium means this thing is equal to 1/2. This thing is equal to 1/2. 1 minus exponential to t over tau L equals 0.5. Okay, so we can actually move this to the right, move this to the left. So we have exponential to negative t over tau L equals 0.5, and then we can take the reciprocal of both sides. Okay, so and then we can actually take lateral log on both sides. Take lateral log and then take the reciprocal of the lateral log, okay, or the lateral log of the reciprocal of both sides. So on the left side we will have t over tau L, okay, because 1 over this thing with a negative exponent become a positive exponent, and then take the log and then we'll cancel this e. Okay, so on the left, on the right side, take the reciprocal of 0.5 is 2. So it is a lateral of 2, okay, lateral of 2. Okay, so here we have a t equals tau L lateral of 2. So in this case, it is L over R and then lateral of 2, which is 53 times 10 to negative third power over 0.36 times negative lateral of 2. Okay, so this is actually 0.1 second. 0.1 second. Okay, so this is the answer to this sample problem. Any questions? Okay, so here we'll talk about the energy stored in B field. Energy stored in the B field. Okay, so yeah, actually this is the equation. UB is the energy stored in the B field, which is 1/2 Li squared. Okay, so comparing with the energy stored in the E field, UE, I'm not sure whether you still remember. Okay, in chapter 25, UE is actually 1/2 CV squared. Okay, so yeah, you can somehow see the duality. So this is the energy stored in the E field, energy stored in the E field, and then 1/2 is actually the same thing, same factor, and then C is the circuit component to generate the E field, and then the L is the circuit component to generate the B field, and then yeah. So actually here we use a voltage or the potential difference for the E field, and then here actually, or maybe you can consider the source of the E field is the potential difference, and the source of the B field is actually the current. Okay, because you have a current going through this stuff. Okay, this will generate B field. This will generate B field, and for the capacitor, you have a potential difference plus or something like this, plus or minus V. Okay, you have a potential difference of V, and then you have a plus Q, and then negative Q. So you can generate E field in between. Okay, so this is somehow the duality, and this is a derivation. So we have a DUB. DUB is a small amount of the energy in the B field, so which will be the P, yeah, and which is I times V, and then I times V is actually V equals L di dt, as we learned previously. Okay, and then we can do the I think actually, yeah, so here we have an integration of DUB becomes the total UB, and then integrating from 0 to UB, so maybe we can just have a prime here so that we can distinguish this dummy variable with this full variable. Okay, so in such a way we can just put in this one here. So here we have something like this, and then it's somehow like integrating I. Okay, so we have a half of I squared finally becomes this thing. Okay, so so nothing special. Okay, so here we have another sample problem. Okay, so it says a solenoid has an inductance of with the same value, and the resistance also with the same value. If a 12 volt EMF is applied across the coil, how much energy is stored in the B field after the current has built up its equilibrium value? Okay, so so for the first question is very easy. So we would like to find UB equals half of Li squared. So here we don't know I yet, but we know the EMF, so which is the V. We also know the resistance, so we can make use of the Ohm's law, so we can find I equals E over R, okay, which is 12 volt over 0.35 ohm. Okay, so this is actually 34.38. Okay, so now we know L and I, and then we can plug in here. So this is 1/2 times 53 times 10 to negative third power times 34.3 squared. So this is 31 joule. 31 joule. Okay, so this is pretty easy. Okay, so for the question B, after how many time constant will have this equilibrium energy be stored in the magnetic field, in the B field? Okay, so this is somehow different from the previous sample problem. So for the previous one, it asks you for the current going to half of its equilibrium, and this one is for the energy. But here you can notice that UB half. Okay, UB half is somehow like 1/2 Li half squared. Okay, So which should be 1/2 Li square for the full current. Okay, so here we have a square here. So we can see that the L doesn't change, 1/2 doesn't change. So in such a way we can actually cancel this one and this one. So finally, I have skipped 1/2. Okay, so it should be like 1/2 of this one. Okay, 1/2 of this one. Okay, so this is half of the energy. So which means that it is only 1/2 of this energy. This energy is for the equilibrium situation, equilibrium point. Okay, so this is the full energy. This is half of the full energy. Okay, so actually we can only cancel this part. Okay, so finally we can see that I/2 is actually 1/2 Okay, so this is not half of it. It's only 1/2. 1/2 is like 0.707. Okay, so in such a way we have I equals, let's say this is big I and then 1 minus exponential to negative t over tau L. Okay, in such a way we have 1/2I. Okay, so what we consider this is I/2, and then this becomes T/2. This become a T/2. Okay, so in such a way we have I times 1 minus exponential to t exponential to negative T/2 over tau L. Okay, so so we can move this to the right side and then move this to the left side. So and then we have exponential to negative T/2 over tau L equals 1 minus 1/2. Actually we can simply cancel this capital I. Okay, we can simply cancel this capital I. So we remains this stuff. And similarly, we can do something like this. This is actually square root of 2 minus 1/2, and then we can take the reciprocal on both sides and then take the lateral log on both sides. So we can have finally we have T/2 equals lateral log of square root of 2 over square root of 2 minus 1, and then we still have this tau L. Okay, tau L. Okay, what we actually did is take the reciprocal and then take the lateral log. So we have this one, and then it becomes this stuff without the negative sign. So finally we just multiply tau L on both sides, so we have this one, and then we can plug in all the numbers. Tau L is actually L over R, which is 53 times 10 to negative third power over 0.35, and then natural log of square root of 2 over square root of 2 minus 1. Or maybe we can just keep this thing because it just asks you how many time constant. So maybe we just keep it here. Maybe we just keep it here. So finally it becomes 1.23 tau L. 1.23 tau L. So this is actually 1.23 times 1.23 time constants. Okay, so here we come back to the energy stored in the B field. And actually, we try to consider the energy density. Okay. So here we suppose we have a long solenoid, and then with a current, so it will generate B field inside the solenoid, and then the current density, the energy density, small UB is actually the UB. UB is the total energy stored in the B field divided by the volume. Okay, this is the volume, AL, and A is the cross-section area, and L is the length of the solenoid. So this is actually a cylinder, and then this is A is the area of a circle, and then the L is the height of the cylinder. Okay, so here we have a UB equals 1/2 Li squared. So here we have a Li squared, and then 2 here, and then AL. And then we can somehow arrange, do some algebraic calculation. So we have a big L over small l, putting it here. And then the remaining I squared putting here, 2A putting here. And then, previously we already know that capital L over small l is mu 0 n square A. Okay, we have derived this equation before, so we just make use of it and then just put this thing here. And then also the B field generated by the solenoid is mu 0 in. Okay, so in such a way we can have I equals B over mu 0 n. Okay, and then actually we can put this thing here. Okay, so finally we have a UB putting here, and then L over L, big L over small l, mu 0 n square A putting it here. Okay. This one is here, and then finally I square over 2A. So this is I, this I is this one, B over mu 0 n, quantity square over 2A. So finally we can do many of the cancellation. This A cancel with this A. This is n square, cancel with this n square. And then this mu 0 partly cancel with this mu 0 square in the denominator. So here we have 2 mu 0 in the denominator, and then this B square in the numerator. Okay, so finally UB is B square over 2 mu. Okay, so this is the energy density is proportional to the square of the B field. Okay, so if you still remember, UE, what is UE? UE is it is 1/2 epsilon naught E squared. Okay, so this is also satisfying the duality. So UB and UE, okay, the energy density for the E field and B field, and then E and B are the corresponding variable. E and B are the corresponding variable, and then mu 0 and 1 over mu 0, mu 0 and 1 over mu 0. Okay, E and B, and then here, E epsilon 0 and 1 over mu 0 are the corresponding. So it just feel like you change UE to UB, and then 1/2 we make the same, and then epsilon 0 change it to 1 over mu 0, and then E square change it to B square. Okay, it becomes the B field version of the energy density, somehow like this. Okay, so here we talk about something called mutual inductance. Previously we learned something called the self-inductance. 那个叫自感应，这个叫做互感应，这个叫互感应。互感应简单来说，它就是一个变压器或者叫做 transformer 或 transformer。OK， 那 Okay, so actually the equation is somehow similar. To the self-inductance. For the self-inductance, it is actually E equals negative L di dt, or usually I will write it as V equals L di dt. Okay, so E and V just take the opposite sign. So here, if we also try to write it as a V equals something, so it is like V2 equals M di1 dt, and then V1 equals M di2 dt. Okay, so these two are quite similar with this one. So this is actually for the self-induction. So we don't self-induction 自感应 so we don't have 1, 2 for the subscript， 那没有1、2个沙标，就是自己跟自己了，所以我们不需要标1、2。那现在的话有1、2的意思是，如果我们在第一个圈有电流，它就会产生磁场就会通过第二个，那它在改变的话，第二个就会有 EMF， 所以这个就是第二个圈的 EMF。就是在第一个有一个动的电流的话，那第二个圈就会有EMF。反过来说，如果我们把这个电源接在第二个圈也行，接在第二个圈的话，我产生一个动的time varying 的一个 current 啊，那也会在第一个圈有一个磁通量的改变啊，磁通量改变也就会产生EMF 啊，所以它简单说的话，它就是一个变压器。那但这个是一个模型，就是它没有损失。实际现实生活中的那个模型就会更复杂，那我们如果做 IC 的话，就损失的话，可能有30%的能量都会损耗掉的，就是如果30%的话，算是蛮好的。但你要看不同的频率也会不一样。Okay, so here we have another sample problem. Okay. So here it says the figure shows two circular closed packed coils. The smaller is this one, with radius R2 with N2 turns, being coaxial with a larger in the same plane. Coaxial 就是同轴嘛，就是之前有说过的同轴。OK， 就是两个都是圆柱体嘛，所以它们就有轴了。那同轴就是两个轴是share 的。OK。然后 OK, so for question A, derive an expression for the mutual inductance M of this arrangement of these two coils, assuming that R1 is much larger than R2. Okay, so we do some approximation. Otherwise, the integration will be quite complicated. Okay. Okay, so here it means that we have a current I1 here, and then we actually can change this I1 so that it will generate some time varying B field, so that for the electric the magnetic flux of the coil 2 will be time varying. Okay, so here we should try to find the phi 21. Phi 21 means it is B1. Okay, the B field is generated by coil 1, but actually we count the area of the coil 2. Yeah, because the coil 2 try to induce some EMF due to the B1. Okay, so here we try to note that as phi 21. Okay, so so here we also have another equation as m equals n2 and then phi 2 1 over I1. Okay, so where does it come from? Okay, so you can try to imagine for the self-inductance, for the inductor, we have L equals n phi b and then over I. Okay, so for the inductor, we only have a single coil, so we don't need to play with the subscript 1 or 2. Okay, so here, so we try to change this equation from the L, from the inductor to the mutual inductance. So we change L to M, and then for the N, of course N phi B, of course we should consider the coil 2. So here we have N2 times the phi 2 1, this one. And then for the current, actually the B1 comes from the first coil. So here we have I1. Okay, so this one becomes something like this. And then we can just put this one here, So we have N2 B1 A2 over I1. And here we try to make use of BZ equals mu 0 I R square over 2 times R square plus C square to the 3 over 2 power. Where does it come from? This one actually comes from 2926. Okay, actually we have derived that before. It is actually the yeah. So we can somehow consider we have a coil. It will generate B field along this axis. Okay, so and also a limit to this axis for the closed form. Yeah, but here we try to use this one for z equals 0, and also given that R1 is much larger than R2, we will assume that all the B field in actually this is R2. Okay, so we just assume that for this part the B field is uniform, although it is not. But given this assumption, R1 is much larger than R2. Okay, so even though it is not so uniform, but if R1 is so much larger than R2, so in such a way, this part considered to be close to each other, and then we consider this part have a uniform B field. So in such a way, we have B1 is actually equals to N1 times B of 0. B of 0 is this one. We just substitute Z equals to 0. Okay, so this one is somehow simplified to N1 times mu 0 I. Okay, so this one should be I1 over 2 times Z to be 0. So we have R squared to the 3 over 2 power becomes R cubed. Actually R1 cubed. Sorry, R1 cubed. And then also we have this R1 square here. Okay, I've just forgot this one. Okay, so in such a way, this R1 square and R1 cube can be cancelled. So finally, it is this one vanish, and then this cube becomes R1. Okay, so finally it becomes N1 and then mu 0 I1 over 2 R1. Okay, something like this. We have the expression of B1 up till now, and then we also have this one have this M to be like this. Okay, so finally we try to put everything into here so that we can find the expression for the M. Okay, so actually it is like also we have A2 equals pi R2 square. Okay, so it is actually a circle. So this is the area of a circle, and finally M is this one. M is this one. So here we have a N2, and then over I1, N2 over I1. Okay, put it here first, and then we have B1. B1 is actually N1 mu 0 I1 over R1. Okay, over 2R1. Okay, this is the B1. This is the B1. This is B1 to be here. Okay, and then finally we have A2. A2 is pi R2 square. So finally we can do some cancellation. I1 and I1 cancel, and nothing else. Okay, so finally we have a pi. Pi, put it in the front, and then mu 0, and then N1, N2, and then R2 square over 2R1. Okay, something like this. Okay, so it is actually like, yeah, these two is a big constant, and then N1, N2 proportional to the number of turns for both coils, and then proportional to the square of the radius of the second coil, inversely proportional to the first coil. Okay, so for the question B, what is the value of M for these values? Okay, so we just need to plug in all the numbers in. M equals mu 0 N1 mu 0 N1 pi mu 0 N1 N2 R2 square over 2R1. Okay, and then we plug in all the numbers. Pi is 3.14. Okay, actually today is the pi day, and mu 0 is 4 pi times 10 to negative 7, and then N1 N2 are both 1,200, and then square. So R2 is this one, 0.011. Okay, all over, and then square here, and then we have a 2R1, 2 times 0.15. Okay, so it is actually 2.29 millihenry. Okay, it should have the same SI unit as the normal inductor.